Find the stress in the steel in pounds per square inch, just before the concrete cracks. In this problem, a 12-inch by 18-inch concrete beam is reinforced using number 9 size rebar. The compressive stress in the concrete and the yield stress in the steel are provided, as well as the Young's modulus of the steel and the area moment of inertia of the beam. The stress in the steel, sigma s, equals the Young's modulus in the steel times the strain in the steel. The problem statement provides the Young's modulus of the steel, so we're left to determine the strain in the steel, epsilon s. The strain in the steel just prior to the concrete cracking equals the moment which causes the cracking, m sub cr, which will be in units of pounds inches, times the quantity, the depth to steel, minus the depth to the centroid of the uncracked beam, all divided by the Young's modulus of the concrete and the area moment of inertia of the uncracked cross-section. In this equation, we already know the area moment of inertia, I, and the depth to steel, D. We can solve for the Young's modulus of concrete by multiplying 57,000 by the square root of the compressive strength of the concrete. In this equation, the Young's modulus is in units of pounds per inch squared. After plugging in the compressive strength of concrete, the Young's modulus computes to 3.372 times 10 to the 6th pounds per inch squared. The depth to the centroid equals n times a times y summed for all parts of the cross-section divided by n times a summed for all parts of the cross-section. In this equation, n equals the stiffness ratio of the part. This variable is also referred to as the modular ratio. Variable a refers to the area of the part, and variable y refers to the depth to the centroid of the part. Next, we'll define part 1 as the concrete in the beam, and part 2 as the steel rebar in the beam. Therefore, that stiffness ratio for part 1 equals 1, and the stiffness ratio for part 2 equals the Young's modulus of steel divided by the Young's modulus of concrete. After plugging in these moduli values, the stiffness ratio, or modular ratio, for part 2 equals 8.60. Next, we'll write out the summation for the depth to centroid, y sub ut, and plug in the appropriate variables, where 7.6 equals the variable n2 minus 1. This transformation makes it easier to calculate the area and depth to centroid for part 1. The depth to centroid equals 9.74 inches. The last variable we need to calculate the strain in the steel is the moment which causes the concrete to crack, which equals the modulus of rupture, which will be in units of pounds per inch squared, times the area moment of inertia, which is given, all divided by the height of the beam minus the depth to the uncracked centroid. From the figure, the height of the beam is 18 inches, and we can calculate the modulus of rupture as 7.5 times the square root of the compressive strength of the concrete. In this equation, both the modulus of rupture and compressive strength are in units of pounds per square inch. After plugging in 3,500 pounds per square inch, the modulus of rupture equals 443.7 pounds per square inch. Now we can solve for the moment. After the variables are plugged in, the moment equals 3.64 times 10 to the 5th pounds inches. At this point, we can solve for the strain in the steel by plugging in the appropriate variables, and the strain in the steel equals 8.36 times 10 to the 5th. Lastly, we can compute the stress in the steel by multiplying the Young's modulus of the steel by the strain in the steel. After plugging in these variables, the stress in the steel equals 2,424 pounds per inch squared. When reviewing the possible solutions, the answer is A.